Assalamualaikum. Hi. We continue with the stoichiometric equations based on the elemental balance. So for the elemental balance, cell growth obeys the law of conservation of matter. All atoms of C, H, O, N and other elements consumed during growth incorporated into new cells or excreted as product. If the compositions of substrates, products, and cellular material involved in a bioreaction, all are known, a material balance on the bioreaction can be written. Like a chemical reaction, the cell growth also obeys the law of conservation of matter. A typical cellular composition can be represented as CH1.8, O 0.5 and 0.2. So this is the general typical cellular composition for microorganism. Variations in cellular compositions with different types of organisms are shown in table 7.3. Okay, so the general empirical chemical formula for microbes is CH1.8, O oxygen 0.5 and for the element of nitrogen 0.2. This is the general empirical formula, and they also have their specific empirical chemical formula. You can find all these empirical chemical formula in the journals and previous research here in the article. Okay, so this empirical chemical formula need to be included in the stoichiometric equation for the reaction. The figure shows a schematic diagram of a cell when it converts the substrate, oxygen if required, and nitrogen into cell biomass, CO2 and H2O. Remember from chapter 6, we learned about the heat generation by the cell. So here we have heat of combustion of substrate and the cell can produce CO2 and H2O. Okay, cell here means the microbes, the microorganism. Consider the following simplified biological conversion in which no extracellular products other than H2O and CO2 are produced. Okay, this equation shows the stoichiometric equation, a general stoichiometric equation for the fermentation. Okay, so this is the substrate CHMON substrate. Okay, if required oxygen, so there will be an oxygen and the nitrogen sources. Alright, the product will be the biomass, which is the microbes. Okay, because there will be a growing of microbes. Alright, and then there will also be product. Okay, and then the releasing of CO2 and H2O. Okay, so CHMO represents 1 mole of carbohydrate. Okay, most the general substrate being used is carbon based. Okay, mainly is carbohydrate. Okay, in the category of carbohydrate. Alright. So simple elemental balances on C, H, O and N, it will yield these following equations. Alright, where C, you can see from the stoichiometric. Okay, we have one C, alright, at your left side, and then it will be equivalent to C, okay, C of 1C, okay, C, plus E, alright, in the molecule of CO2, the C molecule in CO2, okay, follows by H, O and N, alright. The respiratory quotient, okay, RQ, is the moles of carbon dioxide produced per mole of oxygen being consumed. So it will be based on this stoichiometric. RQ is E, carbon dioxide, per mole of oxygen. Oxygen A. So E over A. Okay. Depends on the number of molecule. Alright. Okay. So it will be based on CO2 over oxygen. So this equation is based on the stoichiometric equation represented by equation 115. Okay, here in the notes. Right. So for other stoichiometric equation, you have to look at the number of molecule, okay, in the stoichiometric. Okay, the degree of reduction in terms of the stoichiometric calculation. We can use the degree of reduction also in order to calculate the stoichiometric element involved. Alright. In more complex bioreaction, as in the formation of extracellular products, an additional stoichiometric coefficient is added for the product, requiring more information. Elemental balances are also lacking in that they provide no information on the energetics of a bioreaction. So to deal with the above, we need to use the proton-electron balances in the bioreaction, which used in the concept of degree of reduction. The degree of reduction, denoted by gamma, for organic compounds is defined as the number of equivalents of available electrons per gram atom of C, carbon. So the available electrons are those that would be transferred to oxygen upon oxidation of a compound to CO2, H2O and NH3. So the degree of reduction are shown here based on the element. Okay, for the carbon, C is equivalent to 4, H1, N -3, O -2, P 5, and S is 6. Okay, the table here, table 7.4, shows the degree of reduction and weight of one carbon equivalent of 1 mole of some substrate and biomass. Okay, so the degree of reduction of any element in compounds is equal to the valence of this element. Example, 4 is the valence for C. C just now, degree of reduction, C is 4. Okay, in CO2 and -3 is the valence of N, because of we're referring to nitrogen. Okay. Alright, let's see the examples. How to calculate the degree of reduction for the substrate. For example, you have methane, okay, as your substrate. Methane, we know that the empirical formula is CH4. So, C there, okay, 1C times by the degree of reduction of C, which is 4, plus hydrogen. Alright, we have 4 molecule of hydrogen here. So, times by the degree of reduction of hydrogen is 1. Okay, then you add up this degree of reductions and you will have the total degree of reductions for the whole molecule. Okay, the whole compound, okay, of substrate. Right? So, a high degree of reduction indicates a low degree of oxidation. Consider the aerobic production of a single extracellular product shown in equation 118. Okay, so here we can see the stoichiometric equations, okay, of a production. Okay, this is an example of a stoichiometric. Okay, so CHMON is the substrate. Okay, CH alpha O beta and gamma here is a biomass. Okay, and we have a product here, DCHX, OY and Z. Okay, this is the product. Okay, the degree of reduction substrate, biomass and product, okay, can be written as the following equations, where substrate can see CHMON. Okay, so the degree of reduction, it will be C1 times degree of reduction of C is 4. Okay, it will be 4. Right? then plus H, the degree of reduction is 1, and then we have M here for the number of molecules. So it will be M, and then you have O. O, the degree of reduction is -2, alright, and then times by N, alright. And same goes to the following of biomass and product. Okay, but you have to note that for CO2, H2O, and NH3, the degree of reduction, it will be 0. The hydrogen elemental balance and the oxygen elemental balance are difficult to use in this bioreaction because water is present in great excess. Okay, because we're preparing all those medium in the water. Okay, so we choose a carbon elemental balance, a nitrogen elemental balance, and an available electron balance. So you need to have this elemental balance of carbon, elemental balance of nitrogen, and available electron balance. Alright, then come up with the equations. Okay, based on this, all this equation came from the stoichiometric. Right, based on the element of carbon, okay, based on the element of nitrogen, and the available electron balance, okay, which is, we know that based on carbon, okay, which has the carbon, alright, and then times by the overall degree of reduction, okay, for the compound, whether it is a substrate, product, or biomass. Okay. Since the hydrogen elemental balance and the oxygen elemental balance cannot be used, then we need 2 more equations to solve for the 7 unknown stoichiometric coefficients. Then you have to use the RQ and yield coefficient to help you to solve the equation and to solve the unknown stoichiometric coefficient. The RQ, respiratory quotient, and yield coefficient will need to be determined by experiment. But for your for the question, for any assessment, the information will be given for you to easily calculate the RQ and yield coefficient. Okay, so note that we have coefficient C of biomass on substrate, okay, by denoted by YXS on a molar basis, and we have yield coefficient, okay, D of product on substrate denoted by YPS also in molar basis. Okay, we can also check other equation, assuming that it is an aerobic growth. We also have energy balance for aerobic growth, which can be used in order to solve any unknown variables or any unknown stoichiometric coefficients. And then, however, equations, okay, the equations of energy balance for aerobic is not independent of the available electron balance equation given by 1, 2, 2. Okay, here in the notes. Okay, since QO, the heat involved per equivalent of available electrons transferred to oxygen is constant.